Hi, everybody. Welcome to this talk in the Midwest Computability Seminar on May 4. I'm going to talk about computability theoretic analogs of combinatorial cardinal characteristics, reporting on joint work with Joseph Miller, Stefan Lamp, and Maria Soskova that started in 2019. So far, the paper's available as a preprint. The work started actually by me visiting the Oaxaca workshop on cardinal characteristics in August 2019, and after I went to a research visit in Madison where all this happened. The paper is going to be submitted soon, though it has been sitting there for quite a while already. So first, let's look at the set theory side. Cardinal characteristics measure the deviation of our universe from satisfying CH. They are natural cardinals between omega and 2 to the omega, and always strictly larger than omega. Something like this. Okay, all is 0. For instance, B, the domination number, unbounding number, sorry. The unbounding number. D is the domination number, which is above B, and here is 2 to the Aleph 0. So I'm asking what's between and above Aleph 0, but at most 2 to the Aleph 0, natural properties of the continuum or the power set of the natural numbers provide such examples. For instance, how many functions do I need so that not a single function dominates them all? Where function means functions on omega, and domination is eventual domination. And that's by definition B. In this talk, I mainly consider characteristics based on the almost inclusion relation for subsets of omega. And they have been studied just as long. For instance, the almost disjointless number denoted A is the least size of a maximal almost disjoint family of subsets of omega, where almost disjoint means that any two sets in a family that aren't equal have a finite intersection. One studies CFC relations and also separations for these characteristics. For instance, recalling B and A, it is an easy fact that B is less than or equal to A in every model of CFC. I recorded a proof of that on the Logic blog 2019, because it's maybe a bit hard to find one in the literature, but it's certainly well known. What do I do to prove this? Well, I want to show B is less than A, meaning if I have a set V that's almost disjoint and V size is less than B, then V is not maximally almost disjoint. That's what it means. And to prove this, from every element of V, I produce a function, and a function dominating. All these functions will lead to another set that's not in V and almost disjoint from every of the sets in V. 3 more cardinal characteristics will be important for this talk. First, the ultrafilter number, the least size of a set so that the upward closure is a free ultrafilter on omega. Tower number, the least size of a linearly ordered subsets of the infinite subsets of omega that cannot be extended by putting another element below all of the given sets in that tower. Such a thing is called a tower. The independence number, well, I'll get back to that, but it's briefly speaking the least size of a maximal independent set in the Boolean algebra of subsets of n or omega mod finite difference. Independent means any non-trivial Boolean combination produces an infinite set. This diagram, due to Sukup, displays all the DFC relations, and in most cases separations have been obtained. So you see U and I are incomparable. B is below D, which is below I. And there's a few more that have been studied in computability, such as the unreaping and splitting numbers, R and S. In a paper in the Asian Logic Colloquium 2014, which I think added quite a bit of popularity to this connection of cardinal characteristics and computability. We studied those numbers near the end of the paper in the setting of computability. Also, the escaping number of Brentler and Shelar has been studied by two medicine people, Valverde and Tweed, in a paper 2017. Those were PhD students, I think. P equals T. P is the pseudo intersection number. Shelar and Malyares showed a surprising CFC equality of those two things. So our basic objects are collections of infinite computable sets in the context of almost inclusion. I have to encode these families or collections by a single set. And one common way to do that is as the columns of a fixed set F. The columns are defined as usual. Note that this adds an ordering to the collection of sets. But as we want to study the complexity of collections, we have to do something to turn them into oracles. So it's, I think, the canonical way to do that. I can't think of any other way, I have to admit. Now, we want to compare the complexity of the analogs of cardinal characteristics, and that means of classes of encoding sets of families. So the natural setting is mass problems. A mass problem is a set of functions on the natural numbers. And now we view properties of our encoded collections as mass problems by simply looking at the characteristic functions of the encoding sets. Given that there are no mass problems, we have the usual Muchnik and stronger uniform Medvedev reducibility at our disposal. Recall C is strongly or Medvedev below D if there's a single Turing functional phi that for each element of D produces an element of C. The hardest mass problem is the empty set, has no solution at all, and the easiest is the full set of functions on omega. The question is now, do the ZFC relations of our characteristics somehow lead or correspond to reductions of their analogs? Sometimes they will, sometimes not. So this is really not as close an analogy as the one for cardinal characteristics based on relations, as in our paper from 2014 with Brentler and several later papers such as Greenberg, Kuiper, and Turetsky, who gave a systematic introduction to this analogy, also based on work of Ruprecht, where in his 2010 thesis a lot of things started. So let's introduce the mass problems A and T and see what we can find out about their complexities. Once again, almost disjoint means any two distinct sets have finite intersection, and now I identify collections often with the set describing the collection via the columns. So I say F is almost disjoint if the described collection is almost disjoint, and I only want sets where all the columns are computable. So I want to say that each Fn is infinite computable, and for n unequal k, Fn and Fk have finite intersection. Given that, the math problem A is all the sets F, so that Cf is maximally almost disjoint for the computable sets. That means I cannot find another infinite computable set that would have finite intersection with all the Fn's. It has to hit one of the Fn's infinitely large. It's easy to see that no math set F is computable. Just take some kind of diagonal, right? Here are all the columns, and I take a set that cuts through diagonally, meeting any Fn in only one element, but it's infinite because I can pick one element from each column. That's not in the previous columns. So that that way I get a new set that's computable and has single intersection, finite intersection with each of the Fn's. The problem of maximal towers I describe next. These towers grow downwards, just like in set theory, such as the inverted Burj Khalifa here on this picture. G is a tower if each Gn is computable, each column is computable, and the next column is almost included in the previous column, but the difference is infinite. Gn has infinitely many elements that are not anymore in Gn plus 1. And now T is the class of sets G, so that Cg is a tower that's maximal. In other words, for any infinite computable set R, it fails to be included in all of the Gn's, so there's some Gn, so that R without Gn is infinite. It's not hard to check that A and T are Medvedev equivalent. Let's just do the second one. T is strongly below A. Well, if I have a set F, take pretty much the complement column-wise. So take the set G, so that Gn is the complement of the union of the first n columns of F. Clearly, if F is AD, G is a tower. And if F is mad, then it's a maximal tower, as in this picture. G3 is, for instance, everything that's left after I've taken F0, F1, and F2. That's clearly a tower, and F being a maximally a almost disjoint means the tower is maximal. So these are really not different problems, and I can take whatever is convenient, the version that's convenient. So now I take T, I could also take A, but why not take T? The notation gets a bit simpler. Any non-low oracle computes a set in T, and it's by a fixed reduction. In other words, there's a Medvedev reduction of T to non-low. How do we show that? Identifying strings with the corresponding binary numbers. I am optimizing. I define a Turing functional phi for the Medvedev reduction. Phi z is G, where the nth column of G is all the x's so that x is longer than n, says, and x guesses the first n bits of z prime at s. So that's the definition. And let me try a picture here. That's the binary tree level n. Here we may have at stage s z prime s up to n, and much longer here is s. So all the strings extending that initial segment of length n, all these x's will be in Gn. Eventually, C prime up to n settles at the large enough stage S, I mean relative to Z, of course, and then I just will extend the same cone forever. That makes the set computable. Gn is computable. Also, each time I determine another bit, so the difference must be infinite. Now, if R is a subset of all Gn with finitely many exception numbers, so R star included in Gn for each n, R is infinite, then I can approximate Z prime by taking the limit over all x in R, x of k, where x is longer than k. Simply because R is in G k plus 1. That shows Z prime is touring below R prime, and hence R is not computable, assuming that Z is non-low. A C-MAD set can be obtained by finitary priority construction, which is not too unlike from the construction of post-simple set taught in undergrad computability. The only difference is really that I have these columns now, and I want to distribute infinite CE sets so that they hit one column infinitely often. So think of VE as WE for a moment. So then Pn just reads for n equals ek. If WE without the first n columns of the set S I'm building is infinite, then I put at least k numbers from VE into SE. I do that in a canonical way, but also taking care of that the union of the SIs is co-infinite. That's needed somewhere down the verification. I combine it with permitting, so I can satisfy all these requirements. To ensure each SE is infinite, I actually have to do a bit more. I don't know what VE is, but if I make every other VE just the natural numbers, then I ensure enough gets shoveled into the odd SEs, and I simply say FE is the union of S2E and S2E plus 1. And that takes care of each column of F being infinite. All right, so it's easy to make CE-MAD sets. So what about oracles that don't compute a MAD set? We have seen that they have to be non-computable. I mean, we have seen that no MAD set can be computable, but maybe every incomputable set computes a MAD set. Do we know that? The answer is no. There are other oracles that are non-computable but don't compute a MAD set. Examples are the index guessable oracles. And what we use here is that if you have a MAD set, then the indices for the columns, even though they're computable, are hard to compute. So an index, a characteristic index for a set M, meaning simply an E, so that phi E equals the characteristic function of M, that is hard to compute for those columns. If F is MAD, maximally almost disjoint, 0 prime cannot compute such an index. quick proof. If it could, then I would use an approximation, a computable approximation for the index, and that eventually gives the right number, eventually gives the right index, and I can from then on actually copy the right set into a modified form of f, call it f hat. So each column of f hat is star equal to the column of f. But on the other hand, f hat is computable, so it cannot be MID, though it should be, because MID doesn't depend on finite variance of the columns. So I encapsulate this property now into my definition of index guessable oracles. At some point they were called totally low. L is called index guessable if whenever phi L is computable, then 0 prime can compute an index for its characteristic function. In other words, there's a fixed drawing function on gamma, depending on L only, so that gamma of 0 prime and E is an index for phi L. This property implies lowness, not hard to show. The proposition on the previous slide shows that no index guessable set can compute a maximally almost disjoint set. Since any non-computable C set computes such a set, the C index guessable set must be computable. So which sets are index guessable then? Well, any delta to 1 generic. That's not hard to prove. If F is computable, then we got a sigma 1 set here, CE, the tors, so that at some input phi E tau disagrees with F of that input. This set is not dense along L, else we would get a contradiction to phi E L computing F. So using that and that L is delta 2, I can compute using 0 prime an index for F. And now we have some implications of oracle strength. Delta to 1 generic is downward closed, as you may remember. So we have downward closed classes here. Delta to 1 generic, index guessable, computes no MID, and finally low. We can only separate the last implication because any non-computable C set computes a MED. Take a low non-computable C set to separate the last error. The other two errors, the first 2 errors could reverse, though it seems unlikely. Unlikely because this proof, for instance, used rather a special sigma 1 set. And it seems that I don't need it. I mean, it seems that I don't use the full force of delta to 1 generic. Okay, so that's so much on MID sets. And the second characteristic is the ultrafilter number. I want to introduce a math problem U, which is analog to the ultrafilter number. I look at collections that are towers, and it's more than a maximal tower, a stronger property. Ultrafilter base says that for each computable set R, Fn is almost contained in R or in its complement. So the Fn's generate an ultrafilter in the computable sets, not finite difference. clearly then I cannot extend the tower downwards. So any collection in U is also in T, which trivially implies the Medvedev reduction of T below U, corresponding to the one in cardinal characteristics. And a UFB can easily be obtained by taking R maximal set C, which means that the computable sets R with R union C not cofinite, sorry, R union C cofinite, form an ultrafilter. For each R, either R union C or R bar union C is cofinite. So taking C and using zero double as an oracle, I can produce an ultrafilter base, pretty much asking for each set R that's recursive whether the first or the second alternative holds, which one is cofinite. As a little warm-up, let's see that no ultrafilter base is computably dominated. Well, let G of n be the least number in the intersection of the first FIs. It's basically descending, but not quite so, only up to finite exceptions. So, of course, the intersection of the first n FIs is infinite, so I can define this G of n, the least number greater than n, in that intersection. G is less than or equal, Turing reducible to f. Now, if I have a computable function P that actually dominates G on all inputs, then iterating P yields a sequence of numbers n0, n1, and so on. Now I take the even intervals given by that sequence, call their union E. By definition of G, neither Fn is in E nor is Fn in E complement. So this shows F is not an ultrafilter base. That already shows that not each maximal tower computes an ultrafilter base. Because remember, any non-low set computes a maximal tower. And now I just take a non-low hypermuon free set, which exists. And that will not compute an ultrafilter base. So in the case of ultrafilter bases, I can actually classify the complexity precisely. It is just highness. And for a uniform version, I want to show Medvedev equivalence with the class of dominating functions. So that's a mass problem. The functions H, so that for every computable function, H is almost everywhere above that function. And also for technical reasons, H should be above the identity. TOTS is the indices of total computable functions. And we know that highness means TOT is Turing below F prime. Approximations to TOT are binary 0-1 valued functions, so that the limit over the second argument is the characteristic function of TOT. Martin basically proved, not in that language, but essentially DOM function is Medvedev equivalent to the mass problem of approximations to TOT. That's what we'll use to show that the mass problem DOM function is Medvedev equivalent to the ultrafilter basis, which shows the degrees of those sets are just the high degrees. This happened a lot in Ruprecht's work too, that a lot of things ended up just being highness. Like the whole left lower corner of the Shon diagram collapsed to high in the computability setting. Okay, to show DOM function is strongly below U, we use a lemma we produce a uniformly computable sequence of pi01 classes. So that if phi is total, then the class is a singleton and the element is computable then, of course. Otherwise, PE only contains biimmune elements, so far from computable elements. All these classes are non-empty. And now, if I have an ultrafilter base F, using that sequence of pi01 classes, I know that phi E is total just if for some I and some n, Fi without the exception interval 0 to n is a subset of some x and PE or its complement. And now by quantifier counting, this shows that I can uniformly from F compute an approximation to Todd. Right? This says when phi E is total, and approximating this and a bit of definability in the arithmetical hierarchy shows that I get an approximation to Todd. The detail is in the preprint reference to follow. The other reduction is a bit of a direct proof. First, some notation. VEK is all the x's, so that psi E of x answers k, where psi is the listing of the partial computable functions that have domain in initial segment of n. And now I take the ternary tree, and for any alpha on that tree, I enumerate C is set as alpha. So this tells you how the enumeration is done. Need some reading, I'm afraid. And now I define a uniform list of Turing functionals so that if H is a function of the kind that I have here in my given class, the sequence of values of gamma E with that oracle is non-decreasing. And now Fe is the sequence of values, which is then computable. So here's how to define these things. And in the verification, if H is a dominating function, then it turns out Fe is star equivalent to S alpha. And S alpha is basically what's on the tree to get an ultrafilter base. So this is what this definition here does. Take the leftmost choice so that you keep infinite. That's what it says here. So I actually use H to find the path through that ternary tree that gives me an ultrafilter base. That's what it does. A slight modification, well, more than slight, quite a modification of that construction yields a co-CE ultrafilter base, which is quite a bit better than the delta tree one that I constructed so far using R maximal sets. We had needed a further ingredient, namely a little known paper on R maximal sets from 20 years ago by Lam, myself, and Reed Solomon. So that methodology from that paper helped to make a co-CE ultrafilter base. And I think it can also be done using permitting below a high CE set. And probably the degrees are just the high CE degrees then of those ultrafilter bases. But that's maybe better left to somebody's master thesis. Okay, so briefly one slide on maximally independent families. I told you I is also an important cardinal characteristic figuring prominently in work of Jörg Brandle, for instance. And he calls them MIF, maximally independent families. So what is it? I take a sequence and for each binary string, let F sigma be the corresponding Boolean combination of sets in that sequence. The sequence is called independent, or the encoding set is independent. It's for each string sigma, f sigma is infinite. And then you guessed it, maximally independent means an independent sequence of computable sets encoded by f, so that if R is any further computable set, then it will not keep the family independent, meaning there is a sigma so that f sigma is star included in R or in R complement. Modifying the results for ultrafilter basis, we show that I is Medvedev equivalent to dominating functions and therefore indirectly to U. We don't have a direct proof, and as these two properties are quite far apart, it's not quite clear how a natural direct proof would work. So it's I find it interesting actually that we get equivalence of things that are not obviously equivalent, namely I is Medvedev equivalent to DOM functions is equivalent to U. So it would be interesting to see if there's a natural equivalence, meaning not forgetting what a given object was. So that's a little open question for now. Use the ultrafilter base for what it is, namely describing an ultrafilter, and somehow make an independent set from it. This one is not natural because it goes via dominating functions. Okay, enough of that. And briefly, and on my last slide, I want to talk about other Boolean algebras, not the computable sets. We have defined all these analogs on the Boolean algebra of computable sets, but you could also use whatever the arithmetical sets. And well, here I use the K-trivial sets. We show there's a delta 2 ultrafilter basis on the Boolean algebra of K-trivial sets. Given the argument above, we can modify it to work for K-trivials, and which remember are all super low. So this Boolean algebra is not too far from computable. That's why the same proof still works in modified form. Each ultrafilter base for the K-trivials is necessarily high. We use the domination effect by Kuchera and Slayman. Some delta 2 function H dominates all functions that are partial computable in some K-trivial. So that gives the ultrafilter base. And there I show DOM function is Medvedev above U. So you modify that construction to make a delta 2 ultrafilter base. Also, by a proof of Djokovic Stefan, there's a non-high cohesive set, and some techniques from that proof can be shown what happens in the subrecursive setting, namely the primitive recursive sets. We show an oracle computes an ultrafilter base just if its jump is PA relative to 0 prime. So a moderate highness property is equivalent to computing an ultrafilter base for the primitive recursive sets only. All right, finally some references. The preprint of the paper is downloadable on Chris's CDMTCS preprint server. Slides are available. Logic block 2019 contains the bit. And here are 4 papers relating to the build-up to the current work, relational cardinal characteristics and their analogs in computability. Robrecht's thesis started it off And quite recently, there's a paper with Monin that's called Mulchnik degrees and cardinal characteristics. And well, actually also has things on Medvedev degrees. And here we have certain interesting cardinal characteristics related to density, because that paper was relevant to the gamma question. In fact, contains a journal form of Monin's Leaks paper that gives an answer to the gamma question. So the answer to that question, which was open for a few years, is intimately connected to the study of cardinal characteristics and their analogs in computability theory. Thank you. Hope you enjoyed this.